Hello everyone, so today we're going to be going over maximizing the heat transfer of a rectangular flat plate. And we're going to be using that through the Nusselt number with laminar flow using our equation that's given. And the objective is again to maximize heat transfer over this fixed area and why the flow should be perpendicular to the longer edge. So first, we're going to draw out our situation. So we have our rectangular plane with flow, which we'll use blue for, coming in. So this is hitting this side right here, which I'm kind of doing a little squiggly blue line on. And this creates a boundary layer which gives us two different lengths. First is the distance of our boundary layer, which is d, and then this actual length, which is x. So we have our x and our d length. So what actually is the Nusselt number? The Nusselt number is basically heat transfer of convection over heat transfer of conduction over a flat plane. So when we're given our equation of this nux, so it's over this distance of x, 0.332, our ex, so it's our Reynolds number, our x direction to the 1/2 power, and then our Prandtl number to the 1/3. We can really break this down and kind of see where we're going with this. So our Nusselt number, with that heat transfer of convection over heat transfer of conduction, we can represent this by our heat transfer of convection variable times our x, and that's divided by our heat transfer of conduction, which we'll use our k variable of thermal conductivity. So now we can break down our original equation that we're given of this Nusselt number times 0.332 times our Reynolds number in the x direction to the 1/2 times our Prandtl number to the 1/3. So what is our Reynolds number? Reynolds number, as we discussed before, we kind of already know, is our density, our velocity, and then our x. We're in the x direction here, so we're going that way. And that's all divided by our viscosity, or our dynamic viscosity. So next is our Prandtl number, which is represented by PR. Our Prandtl number is a little bit harder, as it's represented by momentum diffusivity over our momentum diffusivity over our thermal diffusivity. So our momentum diffusivity is equal to the dynamic viscosity over our density, and then our thermal diffusivity, which is represented by that alpha, is represented by our k value of thermal conductivity over our density times our heat capacity. So let's put that into our equation. So now we can multiply this out and simplify it even further. So those densities will cancel, and we get dynamic viscosity times heat capacity all over our thermal conductivity. So now that that's kind of shaping out, we can rearrange some of these and plug these back into our Nusselt equation. So I'm going to sit down. So our Nusselt equation looks like this NUX is equal to 0.332, or actually we'll put in our Nusselt number of HK over K is equal to 0.332 times our 1/2 Reynolds number, which we have our density, our velocity, our x value, and then our dynamic viscosity to the 1/2 power, then times our Prandtl number, which is dynamic viscosity, our heat capacity, and then that thermal conductivity to the 1/3 power. So we want to, that's not HK, sorry, HX. We want to separate this H value as our end goal here is to maximize our heat transfer. So we have H value, so we're going to times that K over X on both sides. So we have H is equal to 0.332. We have our PVX to the 1/2, and then our dynamic viscosity, our heat capacity, and thermal conductivity to the 1/3, and then we have this K over X. So a lot of these can cancel each other out. So let's try to cancel out the best we can, but we have to remember that a lot of these are being squared or cubed. So let's simplify this out a little bit. We have 332. So first we have nothing there, get rid of that density there. Yeah, we got nothing for that density. For that velocity, we got nothing. For that x value, we do have something. So we have 1/2 on the top and -1 on the bottom. So that x will be to the negative 1/2. That velocity, or that, what's it called? Our dynamic viscosity, we have 1/2 on the bottom, 1/3 on the top. So we're going to have negative 1/6 on the bottom as 1/2 minus 1/3, 1/6. So our heat capacity is staying the same. Actually, let's put in these. Thinking about it. Our heat capacity is staying at 1/3. And then our K value is at the top, and that's staying at 2/3. So that is our equation. So let's make this a little nicer. We'll put all the 1/2s and 1/2s together. We have PVX. And then we have our U to the negative 1/6. Our heat capacity to the 1/3. And then our K value to the 2/3. So there's our final equation for for the maximized heat transfer of our heat transfer of convection. So why is this important? Why is this equation important for us? So we can look at this and realize that this x value is the negative 1/2. So actually, the length of this is very important to minimizing heat transfer. So because it's in the denominator, it's really the only one in the denominator. I mean, the dynamic viscosity is too, but it's not to the same effect as the length of this is. So when trying to increase heat transfer, we actually want to reduce the length in between each other. So we want to shorten this if we want to increase our heat transfer. It's very paramount that we're able to do this. So essentially, when x is going down, our heat transfer is going up. So just for summary, reduce this, our heat transfer will go up through this plane. Thank you very much.